Greetings, hello, welcome. Let's continue sketching rational functions. In the previous video, we sketched the first function. Now we found out that it looks something like this. Okay, with its vertical asymptote and horizontal asymptote on the origin. At the origin, looks something like that. Okay. That was the first graph. One thing that we forgot to mention was the domain. So just quickly recap on that graph. This was our graph. It had horizontal asymptote at the origin, and it had vertical asymptote also at the origin, and the graph looked like this. Okay, so the domain, this graph would look, well, this would be the domain. This is, okay, let me just indicate, this is positive infinity, and that's negative infinity. That's positive infinity, and down there all the way to negative infinity. Right there is 0. The domain of this function, the rational function, would be from negative infinity all the way, excluding the asymptote at 0, to come from the, and it goes all the way, as you can see, it goes all the way to positive infinity. So what is the domain of a function? These are the values of x referring to the horizontal x-axis. So all the values of x in which the function is defined, in which you get a y value when you substitute in the function. So all the values that will be able to give you an answer in this equation, all the values of x that will give you an answer in this equation, are part of the domain of the function. So they should give you a valid answer. So all those values are the domain. Okay. So what is the domain of this function? Of the rational function? The domain is from minus infinity to 0. We need to exclude 0. So union from 0, positive infinity. Okay. Another way to write it would be, a domain equals to all the values of x except x is not equals to 0. So that will be another way to write it. Alright. Okay, cool. So What about the range of the function? Well, the range would be all the values of y that are defined for the function. So from minus infinity to positive infinity, all the values that give out values of x. Okay, in this case, from minus infinity, positive infinity, minus excluding the asymptote. Okay, asymptote is at 0. So range will be from minus infinity, 0, union from 0, positive infinity. Okay, this is a curly bracket, I mean round bracket. You can also write it as all the values of x. No, it's not x, it's y. All values of y except for y equals to 0. Okay, cool. What's next? Alright, let's look at the next function. Example 2. G of x is equals to 3x, this one. 3x or x minus 1. G of x, 3x over x minus 1. Okay, let's get the vertical asymptote. Vertical asymptote are the zeros of the denominator. Okay, let me rephrase that. The vertical asymptote lies or is located at the zeros of the denominator. To get the zeros of the denominator, you equate the denominator to 0 and then you solve for x. Right, in this case, x, the 0 of the denominator, x is equals to 1. So the 0, which is 1, is the 0 for denominator, informs us that the vertical asymptote lies at 1. So the vertical asymptote for this function lies at 1. Cool. What about the horizontal asymptote? The horizontal asymptote, we look at the degree of the polynomial. Looking at this, all the polynomials are of the degree 1. So if all the polynomials are of the degree 1, then we divide the coefficient of the highest of the highest degrees, okay, of the variables with the highest degree. So we divide the coefficient of the polynomials, the numerator of the variable with the highest degree, and the denominator is coefficient of the variable with the highest degree. This is what I'm saying. We divide 3 by 1 because there's 1 here as a coefficient of x. So this will be 3 over 1. That gives us 3. So there's a vertical asymptote at y is equals to 3. Okay. Just have our Cartesian plan there drawn already. Then let's look at the x-intercept. X-intercept is found by equating the entire equation to 0 when I'm just saying when y is 0, find x. Okay, so let's just quickly do that. 3x over x minus 1. So 0 multiplied by x minus 1 equals to 3x. So x is equals to 0. So when y is 0, x is 0. Alright, fine, cool. Okay, 0, 0. What about the y-intercept? Okay, y-intercept is found when x is 0. What's the y-intercept? So in this case we have g of x. G of x, something as y equals to 3 multiplied by 0 divided by 0 minus 1. So everything divided by 0, I'm divided by negative 1. Negative 1 equals to 0, so it's 0 as well. Okay, so the x-intercept and the y-intercept more or less the same. So let's plot our points. Okay, vertical asymptote is that x is equals to 1. So it's somewhere there. So let's just have our vertical asymptote right there. X is equals to 1. And our horizontal asymptote is that y is equals to 3. So when y is 3, we have vertical asymptote. Y is 3. Okay, cool. So okay, so x-intercept at 0, 0. X-intercept is at 0, 0. So this x-intercept and y-intercept at 0. They are all at 0, 0, just right there at the origin. But then how do we know the shape of the graph? Because x-intercept is not enough. It's not sufficient data to tell us the shape of the graph. How do we know? How does the graph look like as x approaches negative infinity? How does it look like as x approaches 0? Or as x approaches positive infinity? How does the graph look like? How does it look like? What is the shape of the graph? Okay, so to get that, we need to look at some points on either side of the asymptotes. We have this point, let's call it point A. That doesn't give us enough information. So let's get some extra points. So this is 0. Okay, let's look at the behavior of the graph as x approaches negative infinity. As x approaches negative infinity, let's look at how the graph behaves. And as x approaches, as y approaches negative infinity, what is the behavior of the graph? So to get the behavior of the graph, we substitute points in this side of the on this side of the asymptote. So this is 1. So let's say, let's get a point here. Let's get a point here. Call it 0.5. 0.5. And let's say this is -1 and -3. Okay, so what is g of x? G of x, when, let's say that lays 0, what's g of x when x is -1? Let's start with that one. 1, 1. So that tells us g of x -3 over -1 minus 1, -2. So that is 3 over 2, 1.5. 1.5. Interesting. Okay, if it's -1, we have 1.5. -3. Oh, -3. That's -3 divided by -3 minus 1. That's -4. So -3 multiplied by -3. That gives me -9 over -4 is 9 divided by 4. 9 over 4. 9 divided by 2 gives us 4. 9 divided by 2, that's 4.5. 0.5 divided by 2. 4.5 divided by 2 gives us 2.25. Okay, so 9 over 4 is the same thing as 2.25. Okay, cool. So from here you can see the behavior of this function, that it approaches negative, it approaches 3 as okay, so it approaches 3 as it approaches our horizontal asymptote as x approaches -infinity. So that will tell me that graph is also over there. So it approaches the horizontal asymptote as x approaches -infinity. It also approaches what is it, the vertical asymptote as y approaches infinity. So some story there. Okay, we can also test out some points this side, just 2 points. Let's test out 1, 1.5 and 3. I need 1.5, let's just say 2 and 3. Okay, let's test that out. Change the color to to, well, whatever this color is. 3 multiplied by 2 divided by 2 minus 1. Okay, so 6 divided by 1 gives me 6. Okay, so this is 6. Let's see. Okay, when it's 2, probably let's just say that is 6. 6 is right there. Okay, let's say when the graph is 3, x is 3, so that's 3 by 3 divided by 3 minus 1 is 2, and 9 over 2, that is 4.5. 4.5, probably let's say 4.5 is here. 4.5. Okay, so there you have it. Just 2 points are enough to tell us that this graph is actually in that direction. So this graph on the positive side, okay, or after the vertical asymptote, in the first quadrant, we see that the graph approaches the vertical asymptote as y approaches positive infinity. At the same time, it approaches the horizontal asymptote. You can see here, to keep approaching the horizontal asymptote as the horizontal asymptote, or as x approaches infinity. Okay, all right. So what's the domain? Now what's the domain? Cool. Let's get the domain. So the domain is from all the values from minus infinity all the way to 1 union 1 all the way to positive infinity, which you can also write as all the values of x are valid for our rational function, except for x should not be equal, except for the zeros of the denominator, which is except for 1. X should not be equal to 1, so it's the same thing. You can pick whichever one you prefer, but it's the same thing. And the range is from minus infinity 0 and union 3 to positive infinity, which you can also write as all the values of y are valid except for y should not be equal to 3. Okay, let's test it out. Let's say given g of x is equals to y is equals to 3 3x divided by x minus 1 Let's make y subject of the formula in this case. Well, y is the subject of the formula. I meant to say let's make x subject of the formula. 1 3x. The reason I'm doing this is I want to find out the issue if what I wrote there is correct regarding the range. Okay, x minus y is equal to 3x. Alright. Alright. Now x minus 3x is equals to y. For me, I take out x, factor out x. The y minus 3 is equals to y, and then x divided by y minus 3, we will have y over y minus 3. Okay, so if y was 3, what will be our answer? If y was 3, this will be 3 minus 3, which is 0, and 3 over 0 gives us undefined. So it's undefined on a calculator, so it's infinity. So there you have it. This exactly is our horizontal asymptote. So this is very correct. So cool. The math never goes wrong. It's so cool and it never goes wrong. uh, Trust the math, guys, okay? Trust the math. It never goes down. Never lets you down. Alright. So now we just sketch the last portion. Where is that guy? Yeah. Let's sketch the last one. 2x plus 1. It's not necessary. Let me give that one to you as homework. Try sketching that one, and I'll make a video where I sketch this one and a couple of more complicated ones. So, alright, thank you for tuning in.